the second of two videos in Chapter 19, and this one deals with the ideal gas law. A low-density gas is called an ideal gas. By ideal, we mean that the constituents of the gas are not necessarily interacting with each other. And there's quite a few gases that can actually fit this description, so this law can be valid. The equation of state for an ideal gas is PV equals nRT. P is the pressure, V is the volume of the gas, N is the number of moles, R is a constant, a gas constant, and T is the temperature. So the pressure and the volume are proportional to the temperature. So P is pressure, V is volume, T is the temperature, and those are variables of state. R is the gas constant for the gas, and N is the number of moles of the gas. The number of moles is the total mass of the gas divided by the molecular weight of the gas. How much mass there is per 1 mole of the gas. So M is the total mass of the gas. M is the molar mass, kilograms per mole of the gas. If P is measured in pascals, newtons per meter squared, and V is measured in cubic meters, then our gas constant, R, is 8.31 joules per mole per degree Kelvin, or per Kelvin. So 8.31 is the gas constant if the pressure is in pascals and V is in cubic meters, the basic SI units. But if we measure pressure in atmospheres and volume is in liters, 10 to the minus 3 cubic meters, then our gas constant changes a little bit. It is 0.0821 liter atmospheres per mole Kelvin. The slight difference in the structure of 8.31 to 0.0821 has to do mainly with the conversion of atmospheres to pascals, which is 1.015 times 10 to the 5. So it's not exactly 1 times 10 to the 5, and that's why the number changes a little bit. But you wish to memorize these two gas constants, one for purely SI system, the other one if you're using atmospheres and liters. So what is the volume of 1 mole of gas at standard pressure, 1 atmosphere, and standard temperature, 0 degrees Celsius, or 273 Kelvin? So here's our PV equals nRT, and using this formula in this form, we want to make sure our temperatures are in Kelvin. Our volume will be equal to the number of moles, 1, times R. We're going to use the R because we're given the pressure in atmospheres. So we got 0.0821 for that. Temperature in Kelvin, 273. And our pressure was 1 atmosphere. So this is 22.4 liters. And since we use that gas constant, we have to have our volume in terms of liters. But this would be the standard volume of an ideal gas at standard pressure and temperature. True for any ideal gas that were conditions. Note that if we had any particular enclosed gas, the amount of gas would be constant, so the number of moles would be constant. And hence, under this special condition, our initial pressure and initial volume would be nRT initial, but so our final pressure and final volume would be the same nRT final. So we could divide these two, get rid of the number of moles and our gas constant, and we would have this nice expression. Our initial pressure times our initial volume over our initial temperature is a constant, equal to our final pressure, final volume, over the final temperature. This is only true if the number of moles of the gas doesn't change, which is probably true in about 95 to 99% of the problems you might look at. You're going to have an enclosed gas, and you're not going to change the amount of the gas that you have inside. So this is a very useful relationship, this PV over T equals a constant. You can use it very simply on quite a few ideal gas problems, and this would be very important for you to have. Let's try it out. Pure helium gas is emitted into a leak-proof cylinder containing a movable piston. The initial volume, pressure, and temperature of the gas are 15 liters, 2 atmospheres, and 300 K. Already I know if I were using the gas constant, I'd want to use the 0.0821. However, this is that condition where our number of moles is not going to change, so we can use this PV over T and be just fine with this. So we don't have to know the gas constant. If the volume is decreased to 12 liters and the pressure increases to 3.5 atmospheres, find the final temperature of the gas. So the gas is contained, the number of moles doesn't change, and we can use that ratio so that we don't even have to remember the R value. We have PV over T is equal to PV over T initially, and we want to solve this for the final temperature. So I'm going to bring the final temperature over to the left, and then bring all my other terms over to the right. And so I have my final temperature is equal to my final pressure divided by my final initial pressure, my final volume divided by my initial volume, times the initial temperature. So I have 3.5 atmospheres over 2 atmospheres. Atmospheres cancels out, so I don't have to worry about the units of the pressure. I have 12 liters over my original volume of 15 liters. Liters cancel out, so I don't have to worry about those units. And then times 300 K, which is the initial temperature of the gas. So I'm going to get my final temperature, and the units are going to be in Kelvin, and I come up with 420 Kelvin. So the final temperature of this compressed gas is that the temperature goes up as these particles are moving faster, and that is 420 Kelvin. Avogadro's number. A mole quantity of gas at standard temperature and pressure of 1 atmosphere contains, number sub A is Avogadro's number symbol, and that's equal to 6.022 times 10 to the 23 molecules per mole. Very easy to remember, 6.022 times 10 to the 23 molecules per mole. You might even just say this 6.023 times 10 to the 23, and you won't be off very much if you want to remember it that way. So the number of moles of a gas is the total number of particles we have, N, divided by the number of particles we have per mole, and that would give us how many moles we have. So the total number of particles, N, divided by Avogadro's number, is the number of moles of the gas. N is the total number of molecules of the gas. So we can now rewrite the ideal gas law as PV is equal to little n RT, where little n, number of moles of the gas, is the total number of molecules divided by Avogadro's number. And then if we make a substitution, the gas constant R divided by Avogadro's number is actually another constant called Boltzmann's constant. And Boltzmann's constant is K sub B. So PV is equal to the number of particles, molecules, times Boltzmann's constant, K sub B, times the temperature. Boltzmann's constant is the gas constant divided by Avogadro's number. So we have 8.31 divided by 6.022, and that gives us 1.38. And then 1 over 10 to the 23 will be 10 to the minus 23. So we end up with 1.38 times 10 to the minus 23 joules per Kelvin. We'll note that this K sub B times T will have units of energy, joules, because joules per Kelvin times Kelvin will give us joules. And this will be very useful when we start dealing about the energy of the gas in a later chapter, especially chapter 22. So this K Boltzmann constant will be very important later on. All right, let's try another problem. 1 mole of oxygen gas is at a pressure of 6 atmospheres and a temperature of 27 degrees Celsius, which we immediately want to convert to Kelvin, 300 Kelvin, because any ratios in Celsius is not going to work scientifically, because the Celsius scale can go negative, and that causes a problem for absolute temperatures. So we have to use the Kelvin scale. If the gas is heated at constant volume until the pressure triples, where's the final temperature? So we're going to heat it. The particles are going to move faster. They're going to be at a higher temperature, and it's going to create a larger pressure. Since our number of molecules does not change, our number of moles won't change, and we can use our ratio for this problem. So PV over T is a constant. Let's solve this for the final temperature. Bring that over to the left. Final temperature will be our final pressure divided by our initial pressure times our final volume divided by our initial volume times the initial temperature. Our final pressure is 3 times our initial pressure. We don't know what that was, the value, but it doesn't matter. The pressure and pressure are going to cancel, and the ratio of 3 to 1 is just going to remain. So we're going to have 3. Our final volume will be the same as our initial volume. We didn't know what that was, but that will cancel as well. So the pressures cancel out, volumes cancel out, and we end up with a final temperature as 3 times 300, or 900 Kelvin. If the problem were originally stated in Celsius, then we'd want to convert back to Celsius. So we would subtract 273 from this 900 Kelvin to get a final Celsius temperature. If this gas is heated so that both the pressure and volume are doubled, what would be the final temperature then? Again, we can use our ratios. Final temperature will be the ratio of the final pressure to the initial pressure times the ratio of the final volume to the initial volume times the original temperature. We've increased the pressure to twice as much. The P's cancel out. We've increased the volume to twice as much. The V's cancel out. So we have 2 times 2 times 300, or 1200 Kelvin. So that'll be our final temperature. Again, we can convert that back to Celsius if we wish by subtracting 273.15 from that to get our final temperature in Celsius. It looks like that's what I did here. So 1200 minus 273, final temperature of 927 degrees Celsius. So if you see a problem and they want your final temperature in Celsius, you're going to have to go into Kelvin, work it that way, and then come back to Celsius, unless the problem was dealing with a change in temperature, which we'll deal with later. But if it's absolute temperatures, you got to work in Kelvin. Let's try one more problem. An air bubble has a volume of 1.5 square cubic centimeters when it is released by a submarine 100 meters below the surface of a lake. What is the volume of the bubble when it reaches the surface? Assume that the temperature of the air is in the bubble remains constant during this ascent. So, you're not going to change the number of molecules inside the bubble. And we'll recall that for every 10 meters of depth in pure water, we have an atmosphere. So our pressure, our original pressure is going to be 1 atmosphere. If we go down 100 meters below, we're going to add an atmosphere for every 10 meters we go. So for 100 meters, we're going to add 10 atmospheres. So our initial pressure down below, at 100 meters below, is going to be 11 atmospheres. Our final pressure, which will be the pressure at the surface of the water, will be just atmospheric pressure varying down. So we're going to go from 11 to 1. The content is the same, and so we want to solve this for the final volume. So bring our final volume, multiply both sides by the final temperature, and divide by the final pressure. So our final volume is initial pressure over final pressure times the initial volume. Temperature is the same, we're assuming, so our final and initial are the same, they cancel out. And we have our initial pressure is 11 atmospheres, our final pressure is 1, and our initial volume is 1.5 cubic centimeters. So our final volume will be in the same units, 16.5 cubic centimeters. So you can see the challenge that a diver would have if they were deep underwater as they change their height within the water. The volume of the gas within their body will change. If that volume is dissolved within their bloodstream, those will form bubbles in the bloodstream, and you'll get the condition called the bends. So you can see that this is a problem dealing with, in a sense, the ideal gas law. All right, that concludes our second video in Chapter 19, dealing with the ideal gas law, and we've kept